Good morning, everyone. Welcome to today's webinar about building real-time data pipeline with Declarative SQL. And I'm happy we have Michael today. And together with Michael, we two will talk about why building streaming application is so hard and what are those technologies we can solve this problem and how to build and test and even observe the streaming applications. And yeah, let's start today's session. Let me hand over to Michael. Michael, do you want to make a quick introduction about yourself and what you're building?
Hey, thanks, Gong. I appreciate you having me. Nice to see everybody. My name is Michael. I'm the founder of ShadowTraffic, which is a product that helps simulate production traffic to your backend. Previously, I worked at Confluent as head of product for stream processing. So I've worked in kind of the area with Timeplus for a while. So I'm really looking forward to have a conversation both about stream processing and testing and just how to think about these architectures.
Yeah, thank you, Mike. Yeah, a little bit about myself. I'm CTO and co-founder of Timeplus. Actually been working as a software developer for like 25 years. And yeah, my domain is like AI, BI, big data visualization. So almost every step of building a data applications. So yeah, today and a little bit about Timeplus. Timeplus is a unified like streaming data processing tools, which provide you the real-time data pipelines. So you can use the such data pipeline for building like a real-time analytics, real-time observability like telemetries, and also like a, AI real-time feature like a machine learning feature pipelines. So I will be doing some demo at the end of today's webinars. So, so let's start with this question to Michael. So, why building streaming applications is so hard? Because you are very experienced in streaming data applications. Can you share something about your insight about these questions?
Yeah, I think I've been thinking about this for a long time. I've been involved in streaming since 2013, and I built I built an early open source stream processor. I mean, I think the key thing that just makes these things sort of difficult is that the abstraction is different. When you think about working with a database, you have a table that's frozen in time, and you can run queries on it, and it's like just having an array in memory or a map or whatever, and it's not really going to change on you, and the set of data you're working with is finite. You kind of know everything that's in play, and everything is very I don't want to say deterministic, but very like predictable. But with streams, I mean, when we introduce it to people, the um the analogy that I always use is that it's as if you're working with sort of an infinite array in memory. Like you really never know when the next thing is coming, and it's going to keep coming and coming and coming. And that's kind of the source of a lot of abstraction challenges.
Yeah, I think yeah, it's great that Michael shared his experience, but to me, I think similar. Yeah, Michael built his own stream processing startup before acquired by Confluent. Actually, I see the patterns. There's a lot of people actually are building stream processors. I see our customers before using Timeplus, is actually build their own stream processors. Everybody builds stream processors in some way, and but yeah, but eventually, I think I see that pattern, happens again and again and again. Uh, Eventually, they hit a lot of the streaming application may grow super complex, right? So, so here are something I want to summarize about some of the challenge I see, right? Like one that Michael has mentioned, like continuous data flow or unbounded. So that your data never ends, so it keep coming, right? So that's one of the most significant challenge. Also, like how to handle system failures. So it's easy when you have a single node or single client applications, but when you grow in cluster, it's growing super complex because you have to handle the system failures. Also, as a data, you don't know when data comes, so it's really challenge. You need compromise between latency and accuracy. If you emit fast, you may lose some late arrive events, right? Also, there's a lot of complexity like streaming drawing, streaming aggregations. The logic itself, the stream processing logic itself is super complex. Also, it's like hard to build and operate. When you build it, there are a lot of things to consider, checkpoint, like failures, back pressures, and also you want to monitor what things happening because it's keep running instead of traditional batch applications.
I do think when you think about batch processing, we talk about kind of the negatives about having to recompute everything over and over again, but it is sort of this crutch that like saves you from having to think about a ton of complexity where like, anytime you need to just fix a bug, you just sort of recompute the entire state of the world. And yeah, it's like a little bit wasteful, but it does save you from having to kind of think about how to like avoid duplicating work. But with the stream processing, like it's sort of like if I'm going to replay all that data, will I be retriggering side effects? Like what's the cost of doing that? Will my results still be correct? And I think in the time that I've kind of been part of, this area of computing, it's certainly made much bigger advances. But in the beginning, it was like those were all unsolved questions. And I think that that's kind of been part of the, definitely the complexity battle at making these models easier and easier to use.
Yeah, yeah. Thanks, Mike. Uh, Yeah, actually, yeah, because those challenges, especially the complexity the customer facing when they build the streaming applications, right? So what we want to share is actually why the SQL with declarative has some advantages. So you may see that the comparison between build your own application by writing some code or using declarative SQL to describe what you want. Uh, both solve your problem, right? If you have a stream, like this case, you have a user stream, you want to you can run some code to iterate your records and process it, and you can use the same thing like using SQL. This is what you see, right? But actually, when you're doing a streaming application, it can grow super complex, right? So it's a already highly simplified code. But you can see you need to consider the state, you need to update state, you need to do the checkpoint, you need handle the network issues or any other cluster errors, and probably you want to roll back or recover from your checkpoint something. So the code will grow if you really want to build a resilient, right, a production code, the code might grow super fast. But what we want to do if it is streaming SQL system, most of the system already help you uh, solve those underlying complexity. So what you actually do is, for example, in Timeplus, what you do is actually just create a materials view, and this stream processing framework, the materials view itself will help you to handle those like state management, checkpoint, failover, everything, right? So that's simplify your work. So Michael was the product manager at Confluent, developed the KSQLDB. I think he might have a lot of opinion about developing such SQL-based stream processing uh, compared to like writing your own code. So Michael, what's your idea here?
Yeah, I've kind of gone back and forth about this over time as to what makes sense. And maybe the viewpoint that sort of settled in me is that I think like 80% of the use cases in anything tend to be pretty simple. And that's definitely true in streaming where you have these like kind of point-to-point systems where you maybe need to do some filtering before you put data into like a data warehouse, or you're doing some simple transforms along the way. And I think, at least when I was sort of actively working in this space, I kind of like overlooked those use cases as being like, oh, solved. Okay, let's move on and go do the next thing and do something more complicated. When the reality is it wasn't really solved, and even those use cases were pretty hard. And so there's definitely like room for both of these models. Obviously, at any point in time, you kind of need to exercise all of the layers of the stack to do different things. But I think for those 80% use cases, SQL is really good where you just need to do like these maybe field renames or like I said, simple transforms. Maybe you have kind of a serialization layer that doesn't make sense in one area of the system but does in another. And yeah, to the degree that you can tighten these things up, it's really good. I mean, no one would sort of choose to work at a lower layer of the stack than they actually need to. I do think that the area, like I said, that I kind of committed both faults when I was working in this space, and both under investing in making the SQL tight for those simple use cases, but then also trying to sort of force complicated use cases onto a SQL model. And I think that the area on the left, like if you're going to do something that's like fully at an application layer, where you're doing some kind of like, what would be a good application? Something that does, compensation, for example, and manages different systems. It's just easier to be at these lower levels where you can kind of work with an API directly and have your sort of full debugging tool chain. But yeah, I think, this sort of tech is like anything else where it needs to grow from simple, trustable use cases into ones that are more and more and more mission critical. And starting from SQL is like a pretty good place to just make people comfortable that you don't need to understand checkpointing and you don't need to understand all the things that go into state management. And so yeah, it's like anything else. It's always this gray area. But both models they have needed a lot of work and they are getting better and better. And it's nice to see them pay off.
Yeah, yeah. Thanks, Michael. So yeah, like Michael mentioned, I have some quick pros and cons comparisons. So I'm not saying code is bad. It's actually good, right? You can have a full logic control. You can fine tune your performance. You can do anything because there's a large ecosystem you can leverage, and you can even write some very complex even processing logic with your code. Um, but also, like, not everyone is a developer. We want the streaming processing can be leveraged, can be used by more developers, more users. So even they don't understand how to write code, because learning SQL is much more simpler, right? So with SQL declarative, you don't need to worry about the implementation details, right? So because you just say what you want instead of how to do it, right? Because then you focus on your the problem you want to solve. So it's much more easier to learn, fast to development. We have built-in optimization because the platform under the SQL, whatever is the KSQL DB or Timeplus Proton, we already help you solve this optimization for the performance and manage the code compared to manage SQL. Manage SQL is much simpler because you see there's less code, less you want to worry about, right? So to be short, the SQL we already make the complex thing simpler for the developer, right? Of course, it's a like mentioned, there's nothing perfect, right? There's like SQL has its limitations, like expressiveness is a problem, right? You cannot use SQL to express very complex logic. Sometimes you need some extension, sometimes like iterative SQLs, yeah, it has its limitations, and also something more challenging maybe later Michael will also share with us how to debug, right? Debug SQL is also not an easy job. Debug stream allocation is also very hard. Uh, so yeah, let's quickly share about how build my opinion, our Timeplus idea about building resilience in testable stream application. What we believe is actually with this streaming declarative SQL, we build this stream processing pipeline, and that makes things much simpler, right? So the key issue is SQL, like we discussed, solve the complexity issues. So you don't have to handle those fault tolerant stuff because SQL itself already do it. So test SQL because you can focus on test the result instead of test the procedure, right? So and also we have this standardized error handling and monitoring with our platform. So you don't have to, it's one step. Everything can be monitored. Every error, status, performance, all the reply. There's a lot of metrics you can view from the whole system. Um, yeah, and yeah, last is we make your operation super simple, right? By this kind of abstraction. You can see this is a real use case with a streaming data pipeline. We have external stream read data from Kafka. We do some data extractions, do some drawing, enrichment, do some aggregation and send data to the downstream. So this give you a highlight view of a data pipeline. At the end of today's webinar, I will do some real demo, but next I would like to because after you build this such streaming applications, I think the next big challenge is like Michael and I discussed how to test it, how to verify what you're building is working properly, right? So Michael is building something in this domain, and Michael, so do you want to share something about how building, how you solve the building testing problem in the streaming
Yeah.
app?
Yeah,
Yeah.
just to zoom out, I think this was like a good overview of what the specifics of a stream processor look like. And that's kind of like the backbone of, probably what it is that's powering your architecture. But if we look at kind of, you don't have to switch back, like the last slide, there was a SQL database to the left where we're presumably getting like CDC data out of to go power some sort of materialized view. You can have these models that make it easy to reason and have assumptions and assertions, but at the end of the day, you actually need to be able to check that those assertions are going to hold before you go to production. Um, there's really no substitute for actually seeing all of the components of your architecture work well together. And there's kind of two predominant ways to do this. There's integration testing, which virtually everybody invests in and should, where you take a set of your components and you see whether they work well together. And there are many, many tools for doing this well. You would stub out some of these services. Maybe you have like kind of a microservice architecture or a service mesh, and some services can talk to each other. And in isolation, you can see, does this service work well, or does this pair of services work well? And that's a good and useful thing to do. But another thing that's actually quite critical that very few people do is invest in actually testing the entire architecture all at once. And I think everyone would really like to do this. It's obviously a good idea to actually see the totality of your system running under load that's representative of what your customers either already do or what you think that they might do in the future. But the problem is it's kind of hard. I didn't obviously invent simulation testing. It's a really old idea, but I don't really think that there's been a lot of good tools to be able to make this easy. So I built a product called ShadowTraffic, and the idea, just sort of like theoretically, is to have this sort of black box that sits to the left of your architecture. You run everything for real. So you would run, your SQL database, your Kafka instances, your CDC instances. And we want to be able to feed in data that actually mirrors what it is that your customers do on a day-to-day basis. And I think this is really powerful because if we think about like all the things that we just mentioned as far as stream processing, you could have a simple model in SQL that will let you, do checkpointing and state management and good partitioning and high performance. But you really do need to test that before you actually kind of send it out the door. And if you go to the next slide, I think there's a couple things to sort of setting those conditions and as far as sort of the data goes. So you set up your infrastructure, and then to actually like test this stuff, these are kind of the primary obstacles that I see to people having realistic conditions for checking as their architecture going to perform as well as they want it to. Just to go over them like really briefly, the primary problems that I see are that people they test with data that is just far too weak for what they see in the real world. Your data, I don't know who's watching this, but like I would guess that your data is nested and deep. It's kind of gnarly because that's just what it is to have production data. And you do need to emit payloads that are reflective of that. Otherwise, you're really not going to be testing your system to the degree that it's going to operate under normally. Another big one for stream processing is this idea of relational or correlated data. Again, in that architecture we just saw, there are multiple systems that are emitting data downstream into a stream processor, and it's presumably going to join it together and aggregate it. If you want to test that, you actually need those data sets in different systems to have shared identifiers. And again, that's kind of a tricky problem to do, especially at scale. And it's a critical for getting right with simulation testing. Sequential data is another. If you have something like abandoned shopping cart data, like the order with which the events arrives matters. The customer has to go to your website and then look at the item and then navigate away. And you need to check those sequences at scale to make sure that all of the parts of your stream processor are doing whatever it is that they should be doing. Because it's not enough to just see that it's correct once. You need to check many instances that it works concurrently, it works across different nodes. Um, And then, yeah, geospatial data is another one because many different domains that care about where the data actually is resident to and resides. And chaos operations. These stream processors, a big thing that we've talked about over the years is being able to handle duplicate data or out of order data or dropped data on the wire. I ask people all the time, have you tested this? And they always say no. We just assume that it worked. It is good to check. I mean, the vendors that I'm sure Timeplus, you all do a great job at this, but you want to see it for yourself to see how it's going to behave and just to really check all of your assumptions about what's going on. And I think that these are just healthy considerations as you're going to build these bigger architectures and do more ambitious products, and they can definitely help you. So that's kind of my take on setting up, the right conditions for testing.
Sure, yeah. So when I developed Timeplus, I actually also run a lot of simulations, like Michael mentioned, because you need to test, you need to verify your stream application, whether your stream SQL works as expected, right? I did write some test applications. So it's actually the similar concept, like a code with SQL. Instead, I think the ShadowTraffic gave you a declarative language to describe what kind of simulation data you want to have, right? That's exactly similar like the Timeplus declarative pipeline, right? ShadowTraffic gave you a declarative simulation data. I think that's great idea because that makes a developer, you don't have to write your own code, Python, Go, or Java, to write those, to generate those relational data or sequence data or geospatial data. Instead, you just describe what kind of synthetic data you want to have. Am I
Yeah,
right,
yeah, I think
Michael?
yeah, I think that's a good analogy. And I was gonna say
Yeah,
it's sort of like it's both, the I don't want to say it's not that writing code is a pain. Everybody who's watching this, they can write code. It's
yeah,
really the selection of data structures and the design that goes into making all of the features work well in a composite manner. I think people really underestimate how hard it is to take different parts of an API and make sure that no matter how you put them together, you're still going to get a result that tends to make sense. And the lower you go in the stack, the harder it is to control for that. You do trade off expressivity because you kind of bound the space that you're able to sort of say things in your program. But as you go up the stack, like for example, I put a tremendous amount of effort into making this relational feature work really well because as it turns out, you need data structures that work well under a whole variety of different operations. And if you write the code for yourself, it'll work well for like, a small number of data. But like I have plenty of situations that I can show you where it starts to blow up as you
yeah.
increase the data size. And yeah, it does help to sort of put that layer of control as you go higher and higher up stack.
Yeah, yeah. I believe it's similar like the streaming SQL, right? It solved the scale problem. Yeah, you can solve a small problem, but it doesn't scale if you're writing your own code. But with SQL or with this ShadowTraffic descriptive tools, so it does scale well, right?
Yeah, makes sense.
Okay, so next, I would like to share some of those, like I share about streaming SQL declarative pipeline, but I would like to share some real use cases that actually well, how the customer build with this streaming data pipeline, right? So there's three cases I'm going to share with you. The first is actually a financial service use case. The customer using, there are two issues. One is real-time reporting. They actually want to know the real-time profit and loss, and they can make decisions based on the real-time profit and loss. So the other is like a risk monitoring, like what is there any risk in the trading? Uh, so what they do is they actually build this kind of streaming data pipeline. This is a highly abstracted one. The real pipeline is actually much more bigger, but they give you the idea that we get data from your marketing data, like or your transaction data, like your orders, your executions, the stock price, and you go do some extractions, do some drawing enrichment. You get the metrics. Using the materials view, you get this materials view is actually the key concept of Timeplus, to keep processing your data as soon as new data has come. So these materials will keep processing your data, generating the real-time metrics or real-time profit and loss. And then you get the customer get the real-time alert if something bad happens, if there's a risk, or it get the real-time profit and loss, and they can make decisions based on the latest values. So this is the first use case. And the second case, like cyber in the cybersecurity area, so they want to do the real-time DDoS detections. So they get all the data from network flows, they get extractions, they define the rule, and all the DDoS rule is actually, it's a rule-based, not a machine learning-based. But all those rules can be described by the SQL, streaming SQL. So as soon as something happens, the materials view will process and generate output according to the rules. So the output is like the DDoS attacker IPs or victim IPs, and the client application will consume this output and send the either block those attackers direct to the network devices or protect the victims as well. So the third case is like this e-commerce customer, like a real-time ETL. The key issue is just like moving data from your transactional database to your data warehouse or BI system, right? They need those data to be processed in real time. So they get Kafka, maybe CDC data from Devism. They got all the data, do the extraction, do the enrichment, and send the data to the target table. For this case, they move data in real time from MySQL to the ClayHouse. This is another use case. They use the streaming data pipeline with SQL. Okay, so that's what I'm going to share today. So last, as Michael is here today, so I would like to ask Michael another questions about the future of streaming applications, because Michael was building different streaming applications. So what's your idea? What will be the next? What's going to happen?
Yeah, that's a good question. I'll keep the answer brief just so that we have enough time for Q&A. But I just say briefly, I think infrastructure tends to move kind of slowly. And I think like continuous abstraction of all of these parts that make building streaming apps kind of hard is just sort of the future. And it doesn't sound particularly glamorous, but I do think that that's what provides value at the end of the day, where the fewer things that you need to think about, the better it goes. It's sort of like React in the early days, where it was like, okay, this is an easier way to build web applications. And the really just the model of having kind of the virtual DOM was just it made you have to think about so many fewer things. And I just think just continuing to work on that kind of stuff is, I don't know, really the key forward. But yeah, just for the sake of taking a few questions, I'll keep my answer to that.
Okay. Yeah. Thank you, Michael. Yeah. If you have any questions, please send to the channel. But before we answer the questions, I would like to make a quick demo about the real-time data pipeline with Timeplus. It's actually a real customer case that customer is using Timeplus to build the real-time machine learning feature processing pipeline for game analytics. So the what I'm going to share is about first, there's several different features like temporal window features, accumulative features, and event-based features. So all the different features represent the complexity of the stream processing. So, but all of them can be handled with SQL, and we do provide unified data processing for both your machine learning training data and inference data. For training, most likely you need the batch data, and for inference, most likely you want to do the real-time inference with your streaming data. So that's exactly what Timeplus can provide. Also, one of the key challenge with Timeplus, you can easily backfill historical data. Either it's a cold start of your data, or you want to rebuild something with some historical data. So also, Timeplus provide a good observability and operation, so you can monitor all the metrics with all the pipeline with the metrics and how the cluster operations. This is a Timeplus. We have this timeline pipeline already built. There's some source data like player actions from the game application data, the player actions, the performance data metrics, and all the transactions like how the customer, the players buy something or spend some time. You can see this is the raw data. It contains like a user ID, session ID, what the user do. And this is the performance data and the transaction data, what user buy. And for all the stream, you actually user can query them. For example, this is the player actions. So contain all the real-time data. And we actually use the materials view to processing the features, real-time feature. For example, this one is 5 minutes player features, contains like a how many match started, how many match completed, the average queue in a 5 minutes 5 minutes window. This is a temper window feature. Like you leverage the stream processing the temper window. And also there's the other features like we have this user game states features. It give you the total game played, first game played, last game played. It's actually a accumulative feature. That means it start processing data from the very first record you have. So keep processing, keep calculating do the aggregation. We use the global aggregation, so give you the accumulative features. And also there's other feature like event-based. They give you like the user total spend in the last 10 transactions, right? We do aggregation here, like a group array, last 10 event. So it's event-based. So for every users, we actually aggregate the several events based on the event sequence. So do this kind of features. So all these different features, we actually can calculate them in real time, and we do some we can join all these feature together, and you get a big feature pipeline, all the features in one view using the as-all join. So you can use this view for the training or inference, right? Another thing you can see that we actually do some backup pipeline that moving the data from user actions to up to S3 in real time. So that means we save the historical data to another external storage. That means we can easily backfill this data. So when you do another code start, or you want to recompute something from historical data, you can easily import those historical data from the external storage like S3. So like you see here are all the SQL we use to build this pipeline, everything in this SQL. So like all the features like temporal window features, accumulative features, and you know the record-based features, and as-all join to group all the features together in one view, and you can do the back view here with the S3 or other external database as your backfill historical data, right? And it's easy like just insert the historical data back to your stream to do the backfill. And now you can see we do provide those observabilities. All the materials view, you have quite a lot of metrics and status. You can monitor the performance status, the lagging status, the errors, all the status you have for all your materials views. So you can monitor the real-time status of all your materials views. You see this is one of the material views. You can view the throughput. Uh, and last, you can see we also give you the observability about the whole Timeplus cluster. There's a three node cluster. You know all the metrics, the resources, workloads, every details you can have to control. So give the user the flexibility, and it's easy to use tools to monitor to do the operations. Yeah, that's my demo, and thank you for joining us today.
Thanks for having me
Okay.
on, Gong. I really appreciate it.
Yeah, really, yeah. Thank you, Michael, and it's my honor to have you today. And yeah, thank you.